Hi everyone, I'm Dan and I'm presenting some results on evaluating the fairness of different fine-tuning strategies in self-supervised learning. This is work done with some of my colleagues at Apple. Now the question we had really is, how do different self-supervised learning fine-tuning approaches affect downstream task fairness? Now while many definitions of fairness exist, for this work we take fair to mean the worst treated data partition, or demographic, is treated as well as possible by the model. This work came about due to our hypothesis that how you tune your SSL model impacts its downstream fairness. We set out to evaluate this using the SimClear framework, shown on the right. SimClear is a representation learning framework that generates multiple views of images using an augmentation strategy. It then maximizes similarities of these views of the same image whilst minimizing the similarities of views of different images. This is all done without labels. Once this is complete, it is quite typical to further tune the backbone, denoted F, according to a number of strategies. In this work, we evaluate frozen, updating batch normalization, and another number of other strategies for their fairness properties. To perform these evaluations, we used the celeb-A dataset. celeb-A is a facial image dataset with 40 human annotated binary attributes, which I have denoted with calligraphic C. We use these attributes to define binary classification tasks and dataset partitions, allowing fairness to be quantified. Specifically, let f1 of t given c be the f1 score at predicting t given c is true. T is the task and C, let's say, is the partition index, and either of these could be any of the 40 attributes. A single example of this would be the F1 score for predicting bold, given that the image is blurry. We have an equivalent definition for if C is false, i.e. predicting bold if the image is not blurry. Given these two F1 scores, our fairness metric is called F1 worst of T and C, which is the smallest F1 score over the partitions of C and not C for any given task. In total, there are 1,560 allowed combinations of T and C in order for the F1 score to be defined. This allows us to look at the distributional properties of fairness. Our main findings are that, compared with freezing the backbone, SSL frozen, only updating batch normalization statistics improves fairness by 36%. Doing so almost achieves parity with fully fine-tuned self-supervision, whilst being 4.4 times faster to train and using a fraction of the parameters. Crucially, batch normalization statistics must be treated with extreme care in order to ensure fair outcomes. I'm sure many of us are thinking about how to develop models which prioritize fairness whilst maintaining efficiency. If you'd like to chat more about the findings of this research, come and talk to us at our poster. Thanks.